So today we are going to start our discussion. We're going to start from graph theory, that is our max S4. So let's start. So first we have to know about this Königsberg's bridges. So first we have to understand about Königsberg's bridges. Okay, so a lot of things that we have to understand here. Okay, if you consider the city of Königsberg, in the city there are basically 7 bridges. Okay, so you have to understand. First I will just show you how it is going to be there. So here if you see, this is Königsberg's bridges. Here you can see A, B, C, D. There are 4 islands. Okay, A, B, B, C, D. There are 4 islands. Okay, now there are bridges like 1, 2, 3, 4, 5, 6, 7. There are 7 bridges. So the question here was that there is a city with 4 land areas. You can see A, B, C, D. There are 4 land areas and there are 7 bridges which is connecting them. So the question here is, can you walk through the city crossing each bridge exactly one? There should be no repeating and finish anywhere. That means here the question is like, I need to walk all the 7 bridges. Okay, exactly one time only I am able to walk these bridges. Okay, exactly one. And while I'm doing that, I was able to cross every bridges exactly once and cover all of these islands and all of these bridges and reach anywhere. I can reach an A, B, C, D, any island, I don't care. But can we do this? Only one time we can cross one bridge. That is the main condition that you have to understand here. So that was the question. So the Euler came into the picture, and let's see how Euler solved this. Instead of thinking about the map, the Euler simplified it like each land area as a point or a vertex and each bridge as an edge. So the map becomes a graph. So a graph is made up of a lot of vertices and edges connecting these vertices. So what did Euler did? Euler is trying to simplify this problem by considering A, B, C, D our land areas, right? That is the islands. So considering these islands as our vertices and the bridge connecting these islands as edges. Euler treated like this. Then he found out the degree of the land area. Degree means what? The number of edges in one land area. So that means if you consider this A, what would be the degree of A? The number of edges which is there in this vertex A. That is this bridge, this bridge, this bridge. These are the bridges which is connecting with A. Right. So the degree would be the number of bridges which is connecting to A island. Okay, this is our A island. So connecting to A island, what are the number of bridges? This is the degree of the vertex A. So here if you see, A has 1, 2, 3 bridges. So that means the number of vertices, that is the degree of this land area A, is 3 bridges. Now similarly if you see B has 1, 2, 3 bridges connected to it. So it is degree is also 3. C if you see, 1, 2, 3, 4, 5. Okay. Now if you're looking at C, you can see there are 1, 2, 3, 4, 5 bridges, and D if you check, you have 1, 2, 3 bridges. So that means if you see, C has 5 bridges which is odd, D has 3 bridges which is all odd. So all these 4 areas has odd. So there is a Euler rule. Euler has one rule. Okay, a path that uses every bridge exactly once exists. A path should exist there, and that path should contain every bridge exactly once. That is a condition. For such bridge to exist, if there is 0 odd vertex, it is possible. 2 odd vertex also it is possible. But if you have more than 2 odd vertex, like here you can see more than 4 odd vertices are there. So if you have more than 4 odd vertices, it is not possible to get a graph which can cover all these bridges exactly once. We are not able to get a path like that. If you have 0 odd vertex, then you have starting and end position, it is even number of vertices. So that means starting and ending would be same. Two odd vertex means starting and ending would be different. That would be the different possibility here. But here if you say more than two odd vertex, if you have, therefore getting such path, it is not possible. Okay, so here is, if you see, since there are four odd vertices, it is not possible to cross all bridge exactly once. So in this scenario, it is not possible for us to cross through each of these bridges exactly once. See here, how many method you try? I'm starting from here, let's say D, then I reach this bridge A, then I go like this. Okay, then I'm going like this. Okay, fine, this is, now I can't go anywhere, I can't go to bridge B. So for that, maybe I will go like this, like this, like this, but still this bridge is not covered yet. See, however method you tried, you are not able to cross all these bridges exactly once. That scenario would not be possible. From this, mainly our graph theory has originated from this concept. From this concept of this problem, that is the convex bridge problem, where the graph theory and all has come into place. Understood? You have to understand that part. So you have understood conics work, and there are a lot of terms like degree, vertex, edge, and all, which you have to cover in conics work. Okay, so here if you see, you have a graph. If you consider this graph, this graph is G. Okay, graph G is equal to V comma E, means this graph has two important things, V and VE. V is a set of vertices and E is a set of edges. So that is what graph mainly have. So all the graph have this. We can represent it through V and E, where V is the set of vertices, E is the set of edges. So vertex or node, that is each city we have represent as vertex, right? So we have vertex, and the edge is the thing which is connecting between these through vertices. So vertices can be an object or an entity like this, and which is connecting these two vertices are the edges. End vertices, the two vertices and edge connects. That means if you have E1 that can connect two vertices, V1 and V2. End vertices, that is what end vertices means. Okay, degree is the number of edge touching one vertex. So here if you see V1, 1, 2, 3 edges are touching this V1. So that means the degree of this vertex V1 would be 3. So the number of edges which is touching a given vertex is considered to be the degree of the vertex. Okay, self loop is like this. This EH is a self loop between, that is a loop between V1 and V1 itself, starting from V1 and coming to V1 itself. Now parallel edges means what? If you have two vertices, that is if you have two vertices V1 and V2, here if you see this V1 and V2, there is an edge, like E1 is an edge, E2 is an edge. So there are two edges between this vertex V1 and V2, which are, if there is two edges between, two or more edges between that is connecting to exact same pair of vertex V1 and V2, let's say, so they are called as the parallel edges, and this is what self loop. Understood? Now, so we have talked about self loop, parallel edges and all, right? So here a symbol graph is what? If you consider a symbol graph does not have the self loop or parallel edges, right? They are not having this. If in general graphs we can say self loops and parallel edges are allowed, but if you consider symbol graph does not have this self loops and parallel edges. That is a clean definition of the symbol graph. Symbol graph does not have self loop nor parallel edges. That we have to understand. Fine. So here if you see, a graph is an abstract mathematical object. A physical drawing is just a visual aid, and it is not the graph itself. So here you have to understand that graph is the abstract of a mathematical object. It's just the physical drawing. Okay, it's not. It's just the physical drawing is just a visual aid, and it is not the graph. You have to understand that. Why drawing doesn't change the graph. Now here if you see, graph theories which is there, graph theory is used in lot of real world application. If you see, in internet and web pages are considered to be vertices, hyperlinks are considered to be the edges. Internet and web navigation, GPS, cities are considered to be vertices, and the roads connecting these cities are considered to be the weighted edges. Weighted edges means each of these edges, let's say, has a distance. So if it's that case in cities and road, that distance should be considered of each of the edges, right? Social network, people are vertices and friendships are the edges. Biology and medicine, proteins are the vertices, interactions are the edges. These are just the real life world example in which we are basically using the graph. Now computer networks, routers are the vertices, cables are the edges. Transportation, if you see, ports are the vertices, routes are the edges. So in transportation, in the internet and web, where hyperlinks are considered to be edges and web pages are considered to be vertices. Then we have navigation in the GPS or navigation, you have transportation, you have computer networks means routers and cables, right? Routers are considered to be the vertex, cables are considered to be the edges. Then in biology, in medicine and all, proteins and the interactions and all are considered. So in lot of these are the real world example you have to understand. You have the transportation, the GPS navigation, in biology, computer networks we are using it, internet and web we are using the front. We have the social network, right? We people are considered to be the vertices, and the friendship between, the relationship between these are considered to be in the edges. So these are the real world examples in which we basically use the graph. So if you wanted to ever define a graph, you have to represent it in V and E. That you have to understand. We cannot just draw it in a paper. It does not make a graph. That is what we have said in the abstract part, right? Just drawing it in the paper doesn't make it a graph. We are defining the graph by V and E, vertices and edges. That is one important thing that you have to understand. We have already discussed Konigsberg's bridge problem. Now we have different applications here. Electric network, if you see, these are the applications which is given in your textbook, that if we have keep that picture here. If you see electrical networks, graph theory plays a vital role in the analysis and design of electrical network. Here if you see in the resistance and all, we are between these 4 points you're connecting resistance, voltage and all of these things, right? So these can be represented in the form of graph. In electrical networks, can be designing these electrical networks, graph can play a vital role in that. In an electrical circuit, each of these junctions or the connection point can be represented as the vertex, and each of these electrical component, like the electrical components like resistance, voltage, these are considered to be the edges. So this is how electrical network can be connected to graph, right? So graph can play an important role in designing these electrical network, where each of these junctions can be, like each of these junctions or these connections point can be considered as our vertex, and the electrical component which is present between these junctions, like the resistors, capacitors, the source, they can consider to be an edge which is connecting these two vertices. The graphical representation allows complex electrical system to be studied using simple mathematical and topological principle. Like if you have very complex systems, electrical systems like that, it can be studied using this mathematical, by converting it like this, it is much more easy to study this, the principles and all, okay. Then in chemistry, if you see the hydrocarbons chain and all, in a chemical, we will represent the hydrocarbons chain and all like in a graph form, right? Atoms are considered to be the vertices here, right? Atoms, you can, and the bond between them, right? Bond between them, these different atoms can be considered as an edges. So this representation allows chemists to analyze these molecular properties, predict chemical, like this helps to predict their chemical behavior, their molecular property, and study their reaction mechanism. Because of these kind of diagrams, we are able to study the chemistry, their reaction mechanism, different mechanisms we have learned in chemistry. All these are possible because we are able to represent them. In which form? In this form, right? In the form of graph. That is how it becomes easy for us to represent all of these. Fine. So that is the main thing that you have to understand here. Now if you see here, the next thing that we have here is the finite and infinite graph. Here, finite and infinite graph, if you see, here you have a graph G, V comma E. The vertex set is V and edge set is E. May not be finite set. A graph with finite number of vertices. Here, if the number of vertex and number of edges are given to us, it is finite. Because the number of vertex and number of edges we know. Such graphs are finite number of edges and finite number of vertices if you have. They are called as a finite graph. But infinite graph means we doesn't know how many number of edges and how many, like infinite number of edges and vertices are possible. Like this graph we doesn't know, it's like it can go on extent like this. Such graph are called as infinite graph. In the study of finite graphs, then we have to study finite graph, which is much more and we are going to basically focus on our study on finite graph here. But we have to know that there are two kinds of graph, like finite and infinite graph. Now let's see what do we mean by incidence. Incident means this vertex v1 is incident with this edges e1, e2, e7, e8, e4 would also be there. That means these for these because all four of these edges has v1 as one of their endpoint. If one vertex is one endpoint, like if you have this, if you consider this here, if this v1 and v2 has v5 has one edge between them, so v1's end v1 we can say, sorry, v2 we can say is incident with this edge e5, also with edge e2, e1 and e3, because one of the end point of this edge is v2. That is why we can see e2 for e1 and e3 and e5. We can say v2 is incident to these edges. We are saying it like that. So why we are saying this? That is what we have discussed. We are saying this because we have seen here that one of the end point of these vertex is connected to this vertex. One of the end point of these edges are connected to this vertex v2. So that means v2 can be considered as incident to these edges. This is what incident means. Now adjacent edges, then we have adjacent edges. The two non-parallel edges are adjacent if they share a common vertex. They are both incident on the same vertex. e4, e6 are adjacent, both are incident on v4. e4, e6, e4 and e6, if you consider, they are considered to be adjacent, both are incident on v4. But e1 and e6, e1 and e6, e1 and e6, these are not considered to be adjacent because they are sharing no common vertex. So two non-parallel edges, if you consider, they are considered to be adjacent if they share a common vertex. That is, they are both incident on the same vertex. So then we can say they are adjacent edges. So adjacent edges means, here if we see e4 and e6, that is, this is e4, this is e6. These are can be considered as adjacent edges because they both have this one endpoint. They are both incident to this p4. So we call these edges as adjacent edges. Now adjacent vertex means two vertex vi and vj are considered to be adjacent if they are end vertices of the same edge. That means here if you see vertices, if you consider here v1 and v3, v1 and v3 are adjacent vertices because here if you see their end vertices are of same edge ek. Now they have an end vertex, their edges, right, they are considered to be the end vertices of same edge. Here if you see v1 and v4 are not adjacent. v1 and v4, if you consider v1 and v4, V1 and V4 are not adjacent, no direct edge between them. Now, we cannot consider this example. I will show you figure 1.7 in text. If you see, this is the figure. Here, if you see this figure, the study of the adjacent angle will be much more easier. Here if we see, it is given V1 and V4. Check where is V1. V1 is here, V4 is here. There is any edge between them? No. So since if there is no edge between them, then they are not considered to be adjacent vertices. Now V1 and V3 is considered to be adjacent vertices because there is an edge between them. Like that here to check. Adjacent edges means if they both have a common vertex. Here you see E4 and E6 are adjacent. E4 and E6 are adjacent because they both have same end vertex. Now E1 and E6 have two different end vertex. There is no same end vertex for E1 and E6. So E1 and E6 are not adjacent. Okay, that is what. Two, and it also should be considered of the edges which are non-parallel edges. In the parallel edges, they will be of course adjacent, like that condition would work. So adjacent edges are called for those edges which are not parallel. Okay, non-parallel edges. Here if you see, V1 and V5 are not adjacent vertex. Why? V1 and V5 is here. They are not sharing a common edge between this V1 and V5, right? So that is why we cannot consider the V1 and V5 we cannot consider because there is no common end vertex for both of them. Now degree or valency. Degree can also be called as valency. I told you the number of edges coming to an or number of edges which is going or coming to from this vertex V1, which is all we can say the number of edges which is touching one vertex are considered to be that number we will call as valency or degree of that vertex. So here if you see V1, one edge is E8. Now here there are two edges we can consider in E8. Okay, 3, 4, 5. Here we have 5 because self loop we will count as 2 because one is going from it and one is coming from it. So self loop we will consider as there are two edges connecting to this V1. Then E2, that is 2, 3, 4, 5. So there are total 5 vertex. Similarly V2 if you see, so degree would be 5 for V1. V2 if you see 1, 2, 3, 4, 5. V2 also if you see there are 5. Now let's see this V3. 1, 2 only. Okay, V3 1, 2 only. So V3 has the degree as 2 because only 2 edges is touching it. Only in the self loop we will count self loop as 2 because one edge is going away from it and one is coming to it. So self loop we will consider as it has 2 edges, incident edges. Okay. Now isolated vertex is those has degree 0 and pendant vertex is those which has degree 1. Here if you see, V6 is isolated vertex because it has degree 0, no edges connected, which is isolated. Now V5 is pendant vertex because here only one edge is connected to it, that is degree is 1. One edge is connected to it means degree is 1. So that means this is called as pendant vertex or leaf vertex. Pendant is also known as what? End vertex or leaf vertex, that you have to understand. So here if you see in this diagram, we have understood what we mean by isolated vertex and pendant vertex, right? I have already put that diagram here, but I forgot to check it. Fine. Now null graph. In null graph, here is a graph which has a non-empty vertex set V but an empty set E. That is number of, there would be non-empty vertex set, that is vertex set is not empty, that is there would be some vertices there but there would be no edges connecting these vertices. The edge set is 0. Such vertices are called as a null graph. So such graphs are called as a null graph. Here if you see, the vertex set is V1, V2, V3, V4. There are 4 vertices. Vertex set is not empty, but edges is null. There is no edges connecting these. So such graphs are called as what? The null graph. So that we have to understand. Fine. So till this is just the introduction part of module 1. Now we will see the next video. You will see theorems and all. Thank you.